Good afternoon, everyone. This is Advanced Thermodynamics and Combustion course being conducted by IIT Guwahati under the NPTEL program, and we are into the 11th week of this course, and for that we are having this 11th live tutorial session on the basis of contents of this particular week. And the theme of today's discussion and questions will be combustion and flames. Instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati. And my name is Aditya Sharma. I am the teaching assistant for the live tutorial sessions of this course. So we will be starting in another few minutes. So till then, let's wait and then we can start. Thank you. Okay, so we can start with today's session. So, as I've already mentioned, the theme of today's discussion is combustion and flames. So, in this whole series of lectures that are based on combustion, firstly, we were introduced to basic concepts of combustion and then stoichiometry. After that, in the next week, we saw chemical kinetics related to combustion. This was your second week in combustion. After this discussion of chemical kinetics, we saw thermodynamics of these reactive systems that we discussed. Okay, so the thermodynamics of these reactive systems was discussed using some reactors, right? Like well stirred reactor and plug flow reactor. So this has been the discussion up to this point. Now, from this point, uh, we will be discussing, or for the matter of this, as far as this week is concerned. So, here the discussion will mainly revolve around the flames. Okay, so what different types of flames are encountered in different types of combustion, and what are the characteristics of these flames, how these flames behave in different conditions. So all this has been discussed in this particular week, right? So there are total three lectures in this week, lecture 28 to 30. So briefly, first of all, we'll see the topics. After that, we'll see some theoretical questions or conceptual questions, true or false type, fill in the blanks type, multiple choice question type of questions, and after that we will solve some numerical problems. All right. This way we are going to have our this tutorial. So first of all, briefly we'll discuss the topics. So first topic here is modes of combustion. So what different modes of combustion are there? So the lecture says that there are basically two major modes of combustion. One is where your flame is premixed. Second one is where your flame is not premixed, or this is also known as diffusion flame, where the fuel and oxidizer diffuse, and in this way the combustion takes place. And in the case of premixed combustion or premixed flame, the fuel and oxidizer are already mixed, and after that combustion takes place. Okay, so these are two modes of combustion where we have flames. So there can be case that we have no flame. All right. In combustion, there can be flame and there cannot be flame, but this is the case for uh, combustion processes where we have flames, right? So flames basically are subsonic in nature, okay, and they are self-propagating. But there are cases when your combustion wave is supersonic also. All right. In that case, the phenomenon is known as detonation. All right. So if your combustion wave is supersonic, in that case, this is known as detonation. And in case it is subsonic, that is known as deflagration. Combustion is known as deflagration. One example of engines in which detonation takes place is pulse detonation engine, where combustion takes place in the form of detonation. Okay, so in such engines, we use uh, detonation to combust the fuel, and there is some frequency at which this detonation is done in your engine. Okay, so this is your combustion rate. So this I'm discussing the physical features of laminar flame. Okay, so this discussion is on a flame that is laminar in nature. Okay, so there are parameters linked to a flame, like flame speed is there, right? Flame speed, that we denote by SL, correct? Right. And then when so this flame actually is a very thin region, right? So its thickness is of the order of 1 mm, right? So in this flame also there are zones of combustion, right? So one such zone is your preheat zone, and then is your second is your reaction zone. So your flame can be divided into, if you take your flame, it can be divided into preheat zone, and then is your reaction zone. So your reaction zone is the one where your chemical energy is released. Okay, so the release of energy is prominent in this region. Okay. Then next topic is your factors influencing your flame velocity. So your flame has some velocity, and this velocity is, it is not like that for a particular fuel this velocity is always the same. So there are parameters or properties on which this flame velocity depends. All right. So this has been discussed in this topic. So one such is your temperature, and then also your pressure is there. Correct? So your laminar flame has is strongly dependent on your temperature, right? So here it says that the increase in temperature of unburned gases will also increase the temperature of the burned gases. Okay, so temperature has a positive effect on your flame velocity. Then for pressure, it has been seen that for pressure, the dependence is negative for the flame velocity, right? For the temperature, it was strongly dependent, and for this pressure, this is dependence is negative. All right. After that is your equivalence ratio and fuel type. Okay. So this is your equivalence ratio and fuel type. So if you see your hydrogen and propane, so this has been discussed using this example. Okay, so for hydrogen, your flame velocity will be higher if you compare it with propane, which is a hydrocarbon. Okay. So reasons for this are: first is your thermal diffusivity and mass diffusivity, which is higher for your hydrogen, and then your rate, reaction kinetics of hydrogen. So the rate with which reactions take place in hydrogen is very fast. Okay, so these are the two points by virtue of which the flame velocity of hydrogen is higher in comparison to propane. Okay, and for the equivalence ratio, what happens is that as you increase the equivalence ratio, so this trend follows the trend of temperature. So as you increase the equivalence ratio, your flame velocity increases. But this is not valid for your rich mixtures. Okay, so this is valid for your lean mixtures. So this is the effect of all these parameters or properties on the flame velocity. Then next topic is your flame speed correlations. Okay, so one mathematical expression for your laminar burning speed or your flame velocity of a laminar flame. This has been given in this topic and discussed also. Okay. Other than this, there is not much in this topic. All right. So this was your lecture number 28 on modes of flame. Okay, modes of combustion or modes of flame, and then what are the physical features of a laminar flame, and the flame velocity linked to a laminar flame, how different factors affect this velocity. So this was discussion on flames, lecture number 28. Then next, so this is introduction of flames, okay, this lecture. After this, we have lecture number 29, where we discuss that how do we arrest a flame. We have initiated a flame, ignition has started, we have a flame, we have a flame front, but if we have to stop this flame or arrest this flame, the correct terminology is arrest. So if we have to arrest this flame, so how can we do that? First, this has been discussed. Other than this, there is uh, one more topic that is discussed in this lecture, that is your flame stabilization. Okay, so when you want to have combustion of some fuel, so obviously you would want that your combustion must be predictable. Okay, and for predictability, it is in our favor that this flame is stable. Okay, so more the unstability in the flame, more the uncertainty in combustion. So in that case, how we deal with the challenges as far as the flame stabilization is concerned. So this discussion has been done in this flame stabilization. Correct. So first topic is your flame arresting methods. So there are a couple of methods by virtue of which we can arrest our flame, right? So one common method is that you make the passage of your flame very narrow. So if the passage of your flame is very narrow, in that case, flame won't be able to propagate any further, and it will eventually extinguish. Okay. So there are concepts linked to your flame arresting. One is your quenching distance, also is flammability limit, also is your minimum ignition. Minimum ignition has been discussed in ignition analysis topic of this lecture. Okay, so these three things are there. Sorry. First is your quenching distance, then is your flammability, and then is your flammability limit, then is your minimum ignition energy. So one by one we shall see these. So first is your quenching analysis. So first of all, what is a quenching distance? So the critical diameter of a circular tube where the flame extinguishes, okay, is referred to as quenching distance. So this is your definition of quenching distance. So diameter of your circular tube beyond which for which your flame won't propagate is your quenching distance. Correct? So numerical formula also has been given for quenching distance, okay, which is where del is your this is your flame thickness, correct, and this is some constant. So this is your quenching distance. After that is your flammability limits. Okay. Next topic is your flammability limits. So flammability limits, as the name suggests, flammability. So whether your mixture is flammable or not. So this is the whole point here. So this flammability limit is defined based on your equivalence ratio. Okay. So this is defined based on phi, which is your equivalence ratio. So there are two limits. One is lower limit and one is your upper limit. Okay. So phi less than 1 is your lower limit and phi greater than 1 is your upper limit. Phi less than 1, remember, is a lean mixture and phi greater than 1 is a rich mixture. Then next is your ignition analysis. So in ignition analysis, we see this minimum ignition energy. So what is minimum ignition energy? So this is the energy that is added by spark. Okay. So this spark will heat some volume. Okay, so this volume is uh, known as critical volume. All right, and this raises the temperature of the mixture to burn gas temperature. So this is your minimum ignition energy that is required for your combustion. Okay, and in case minimum ignition energy is not provided for a particular critical volume, in that case, the combustion won't take place. All right. And then trends linked to this minimum ignition energy has also been discussed. So what happens? What is the behavior of minimum ignition energy with pressure? Okay, and what is its behavior with temperature? These things have been discussed in this topic. So this is your ignition analysis. What from here, what we have to remember, what is of our focus is the minimum ignition energy. Okay, that this concept we can use to arrest our flame. Okay. After this, the next topic is flame stabilization. So in flame stabilization, there are two things. One is your flashback, and then is your lift off. Lift off. Sorry, lift off. So these both of these are undesirable during combustion. Okay. Flashback can be very disastrous in case of combustion. So if your flame reverses, okay, instead of moving in uh, one particular direction that is desirable, it starts moving in opposite direction. In that case, it can be disastrous. Such situation can be disastrous. All right. So, so in that case, how do we stabilize our flame? Okay. So the same concepts as we used in your flame arresting can be used in your flashback. All right. Because here also, when if a flashback initiates at some time, some point, in that case, sorry. So in that case, how do we arrest this flashback? So that is very critical for us. Then is your lift off, where your flame lifts from the port, okay, from where it originates. So what causes this lift off, and how can we avoid this? Because eventually your lift off can also lead to blow off, right, which will lead to as extinguishing of your extinguishing of your flame. So to avoid that, we need to have knowledge of lift off and then blow off, then how flow velocity takes part in this discussion, right? So all this has been discussed in this particular topic. Correct? So this was your liftoff. After that is your last lecture, which is lecture number 30 of this week. So in this lecture, discussion revolves around laminar jets, okay, or laminar jet flames. The discussion here also is on flames, but the type of flame we here are discussing jet flames. Okay, so in this discussion, first is your non-reacting laminar jet. So what we have done, we have basically idealized this jet by considering non-reacting flows, okay, for our discussion. And then we have done our discussion on laminar jets. So one good example of laminar jet is your cooking ovens, okay, so that we use in our houses. So that is a good example of laminar jets. So one important point of about these laminar jets is that they produce soot, okay, black colored soot. That is basically carbon. So there are cases where this soot gets oxidized, but there are cases where this soot is unable to oxidize. So what happens is it breaks through your flame, and that we see in the form of this black particles. Okay, so this happens in a laminar jet flame. All right. Then is your topic on jet flame mathematical description. So here conservation equations have been used, and then conservation equations like mass conservation equation, then momentum conservation equation, species conservation equation. So all this has been put on the table, and then discussion on the mathematics of these jet flames has been done. All right. So this is your jet flame mathematical description. Then is your laminar diffusion flame structure. So laminar, I'll just draw this. Okay. Something like this. So in this case, your flame front, okay, will be available where your equivalence ratio of your mixture is equal to the stoichiometric equivalence. Where the equivalence ratio is equal to 1. So where your air and fuel, the proportion in which air and fuel are, so they are in the stoichiometric ratio. Correct? and the inner regions, in the inner regions, your equivalence ratio is greater than 1. That is, these are what? This mixture is rich in nature, while the outer one is less than 1, which means this is leaner. Okay, so this is your jet flame, sorry, diffusion flame. All right. After that, the last topic is, so this has been done, this has been done. Then is a conserved scalar. For the concept of conserved scalar, we were introduced in the last week. Okay. So here also we can use the concept of conserved scalar in the form of mixture fraction to analyze our jet flame. Okay. So this concept of conserved scalar in the form of mixture fraction can be applied in your flame sheet also. Okay. And this can be applied beyond your flame sheet also. All right. So this can be done inside the flame sheet, at the flame, and beyond the flame sheet. So this way we can analyze our jet flame using conserved scalar. All right. So this was your last topic. Of this week. After that, we will now move on to questions. So let's see questions one by one. So here is the first question. Please read this question. There are four options and then try to come out to an answer. Okay, so the question is from physical features of a laminar flame. And it says that a flame is a self-sustaining propagation of a dash combustion zone at dash velocities. Okay, so whether your combustion zone is localized or globalized, first is this question, and whether your flame is subsonic or supersonic. Second is this question. So we have well covered this, that your flame is a self-sustaining propagation of a localized combustion zone. It's not a globalized combustion zone, just a thin, very thin region, okay, of the order of 1 mm. So first is your localized. So your answer will be from either from A or B. So either it will be A or it will be B. Then we have also learned that your velocities for your in which the flame velocity in which the flame propagates is subsonic. Okay, so in that case, your A option is correct. Okay, all right. In that case, A option is correct. After that, we will move on to next question. So A option is correct. So this is a statement type of question. A premixed flame is also known as a diffusion flame. So whether this is correct or not, from modes of combustion topic. So there are two types of flames. One is your premixed flame, and another is your non-premixed flame. So out of these, which one is your diffusion flame? And also, what is a diffusion flame? Please try to think on this. So this is pretty straightforward. Diffusion means, so I have discussed this earlier also. Diffusion flame means where your fuel and oxidizer will diffuse, and this diffusion will lead to eventual combustion. Okay, but if the combustion has to take place by means of diffusion, in that case, it shows that your flame is not premixed. Correct? So in that case, if the statement says that a premixed flame is also known as a diffusion flame, this is a false statement. A non-premixed flame is also known as a diffusion flame. Okay. So this is your question number 2. It was on modes of combustion topic. So let's move on to next question then. So read this, please. Read the question, the topic, and then try to answer this. Okay, so the question is on physical features of laminar flame. This is topic of lecture number 28. It says that in hydrocarbon flames with excess air, the fast reactions appear as blue, which is resulted due to excited dash radicals in high temperature zone. So, because of which radicals? the blue color appears in high temperature zones. Whether this is option A, B, C, or D. Okay, so the answer says that this is the CH radicals, but I have one doubt regarding this. So I'll again check if the answer to this question is correct or not. Okay, so as per your lecture slides, it is CH, but then I'll have to again check it. So I'll just check it and then confirm this. Okay. Okay. So then next question is your fourth question. So before we start with the first fourth question, we'll take a short break because it's already 4 p.m. So a quick 5 minutes break we'll take. After that, we'll resume with our session. Okay. Thank you. Okay, so we can continue with the session. I checked for question number 3. The answer is CH radical only. So this is correct. Okay. The blue color in high temperature zones is because of CH radical only. Okay. Then is your next question based on modes of combustion. So whether this statement is correct or not. So the statement says that diesel engine combustion is dominated by diffusion burning only. So whether this statement is correct or not. So in diesel engine combustion, it's a mix of burning. Okay. So the in terms of modes of combustion, both the premixed mode of combustion and then non-premixed or diffusion form of combustion, both have a role to play in the diesel type of engine. So in that case, this becomes a false statement. Both, both mixed and diffusion burn. Okay, then moving on to next question. So this question is on flame stabilization, and these are the options. So this is on flashback stability of methane in comparison to hydrogen. So first read the question carefully and then try to figure out which of the following will be the correct one. So first question is whether the flame stability of methane is higher than hydrogen or lower than hydrogen. First is this question. Okay, then second question is whether the flame speed of methane is higher. So whether the flame speed of methane is higher in comparison to hydrogen or lower. So these are the two questions that we need to address. So we did discuss that for hydrogen the flame speed is very much higher in comparison to propane. Okay, but here we have been asked about methane. So there we said that the reasons for higher velocity, flame velocity was one was mass diffusivity, one was your thermal diffusivity. And then one another point was made in this argument. Okay, so same is the case with hydrogen and methane. For these two, out of these two, for methane, the for sorry hydrogen, the flame speed will be high. Which means lower flame speed of methane in comparison to hydrogen. Okay. And then the flashback stability of methane. So what happens to the flashback stability of methane with this flash velocity? So this higher flash velocity of higher flame velocity of hydrogen contributes to lower flashback stability in comparison to methane. Okay, so which means that your flashback stability of methane is higher. Okay, this has also been shown by means of a graph, which is primary air versus fuel flow velocity. Okay, in it, your flash in this graph, your flashback zone, your lifting flame zone, this has been shown. Okay. So as far as this question number 5 is concerned, your B option should be the correct option. Let's see. Okay, option B is correct. All right. Then we will move on to next question. That is question number 6. So what is deflagration and what is detonation? Based on this knowledge, you will be able to answer this question. So this is from physical features of laminar flame. And the question 6 says that when the discrete combustion wave travels at subsonic speed, it is termed as deflagration, while at supersonic velocities, the wave is referred as detonation. So this is statement says that for subsonic combustion wave, the term used is deflagration, and for the supersonic velocities, the term used is detonation. So if you see this here, combustion wave. So for supersonic it is detonation, and for subsonic it is deflagration. And if you see this, for supersonic it is detonation and subsonic it is deflagration. So in that case, this is a correct statement. Okay. So moving on to next question then. The question again is on physical features of laminar flame. Please read the question and try to figure out the correct option. Okay, so let's see this question. It says that considering the laminar flame, the product density is dash than reactants and the burned gas velocity is dash than velocity of unburned gases. So for your product density in comparison to reactants, it will be lower. Okay, because in reactants you have some fuel and then this fuel is converting into gaseous gaseous form. Okay, and then burned gas velocity is obviously higher than the velocity of unburned gases. So in that case, option B is the correct option. Okay, now moving on to the next question. So this is on physical features of laminar flame. And this is question number 8, which says that the bulk of chemical energy in a laminar flame is released in preheat zone. So we have learned there are two zones. So maybe I'll draw this for the purpose of discussion. So this is a question number 8. Okay, so this graph is like this. So here we will have heat release, then temperature, then mole fraction in different scales. Okay, then is your axial distance. So this is for your mole fraction. Okay, of your reactants, and this is for the temperature. So this is for your mole fraction of reactants, which dips as we move in the axial direction, and this is for your temperature. And this is your heat release. So initially what we see is that, so in your flame, the structure of flame is somewhat like this. This is your preheat zone, and this is your reaction zone. Okay, so from the graph it is visible that the maximum release of heat is in this region. Okay, is in your reaction zone. Correct. So this is your heat release. So maximum it is in this reaction zone. Okay. So when the question or the statement says that the bulk of chemical energy in a laminar flame is released in preheat zone, then it becomes a false statement because it is not preheat but the reaction zone. Okay, this was your eighth question. The answer was B. Now moving on to next question, that is question number 9. This is on physical features of laminar flame again. Sorry. And it states that the fast chemistry region in the laminar flame is dominated by termolar reactions. So whether this is correct or not. So what is this fast chemistry region in a laminar flame? So we saw there is preheat region and then there is the reaction region. But then what is this fast chemistry region? And if this is fast chemistry region, is there also some slow chemistry region in the laminar flame? Is it that? So in your reaction region only, if you see your reaction region, in your reaction region only, there is further subdivision of this zone. Okay, into fast chemistry region and then slow chemistry region. So the region where your fuel molecules destruct, okay, and then new intermediate species are created. So that is your fast chemistry region. And then after that is your wider region, that is slow chemistry region. And this fast chemistry region is mainly dominated by bimolecular reactions. And what are bimolecular reactions? In our elementary reactions discussion, we did discuss this. What are bimolecular reactions? So bimolecular reaction is a type of elementary reaction where you have two species in the left hand side of a particular elementary reaction. Okay. So the answer to this is bimolecular. So B option is correct. This is false statement. Then moving on to the next question. This is based on factors influencing your flame velocity. So it states that the laminar flame speed is independent of temperature, whether this is correct or not. So in the topic factors influencing flame velocity, we have seen that your flame velocity first depends on temperature and pressure, then it depends on equivalence ratio. Yes, and also it depends on one more factor, that is fuel type also. It depends on fuel type also. Okay, so statement says that the laminar flame speed is independent of temperature. We have discussed this, that flame speed or flame velocity very strongly is linked to temperature in such a way that if the temperature increases, the flame velocity increases. Okay, so this will be a false statement. One, I believe it's an empirical formula which is given in the slides. Okay, for your linkage between the link between the flame velocity and then temperature of unburned gases. All right, this is a false statement. Then moving on to next question. So the next question is on factors influencing flame velocity again. So hydrogen has higher thermal diffusivity than propane. So we have discussed this. This is correct, okay? So this higher thermal diffusivity is one of the reasons for hydrogen to have higher flame velocity in comparison to propane. The other factors are flame velocity, mass diffusivity, and then the reaction rate of hydrogen is higher. Okay, so this should be a true statement. So yes, this is a true statement. So this was question number 11. Then moving on to question number 12. This is from flame arresting methods. So it states that allowing flame to pass through narrow passage helps in arresting it. Well, this is correct or not? This is a correct statement. This is one of the fundamentals of arresting a flame. So if you make your passage of the flame narrow, in that case, you are increasing your chances of arresting your flame. Okay. And to what extent you need to make your passage narrow is your quenching distance then. Okay. This is a true statement. Then from ignition analysis, the next question is question number 13. The minimum ignition energy is the energy added by the spark that heats the critical volume to burned gas temperature. Okay. First of all, what is your critical volume? Okay. So it says that the energy given by a spark to attain a temperature of burnt gas. So this temperature has to attain by what? By some critical volume. So what is this critical volume? So critical gas volume radius can be defined such that the flame will not propagate if the actual radius is smaller than the critical value. So if the radius of this volume is smaller than a particular value, in that case your flame will not propagate. Okay, so this is your critical volume. Okay, pertaining to this critical radius. So whether this is correct statement, this is correct statement, no doubt. Okay, so this is the definition of minimum ignition energy. If this amount of energy is not provided to a mixture, in that case, flame propagation won't take place. Okay, flame won't sustain. Right. Then moving on to next question, which is again on ignition analysis. This says that the increase of initial mixture temperature results in increase in ignition energy. So if you increase the initial mixture temperature, so this will result in increase in your ignition energy. So in ignition energy, we saw that the energy we require to ignite our mixture. So this is question number 14. The answer to this question is false. Okay. If we increase the initial mixture temperature, in that case the ignition energy that is required will be less because your mixture is already energized to some extent. We just need to add some more energy to it and then our work is done. Okay, so option B is correct. Then moving on to next question. This is from laminar diffusion flame structure. This states that the hydrocarbon diffusion flames have typical orange-yellow appearance, which is the indication of presence of soot in the flame. The diffusion flame, yes. So this candle is also an example of diffusion flame. Okay, because in candle we have fuel, but then oxidizer is from your surrounding. So these two diffuse and then combustion takes place. So the hydrocarbon diffusion flames have typical this color, which is the indication of presence of soot. So this coloring is because of soot. So this is correct. So this is also correct statement. Okay. If you see the answer, option A is the answer. So these are the questions, theoretical questions, conceptual questions. Now we will move on to, so these are 15, total 15 questions. Now we will move on to some numerical questions. Okay. So this is your information for question number 16 to 18. We have methane gas, which is being leaked at this temperature and pressure. So after some time they are totally mixed. Okay, so this is pre-mixed condition then, pre-mixed mode. The lower and upper flammability, sorry, of this should have been methane here. Is this universal gas constant has been given. Based on this information, we have to solve the upcoming questions. So let's see the questions. First question is find the mole fraction of methane. So what will we do? Find the mole fraction. Mass of fuel is given. R is given. Then temperature is given. Then pressure is given. Then volume of the room is given. Okay, the volume has not been given. So take the volume as dimensions of the room. 2 meter by 2 meter by 3 meter. Okay, take these. So 2 by 2 by 3 is 12 meter cube. All right. Then for methane, molecular weight is what? 12 plus 4 into 1 is 16. Okay. Then we know partial pressure. Methane, that is fuel. So it will be like this. R will be 8314 divided by molecular weight of your fuel, that is methane. So this will come out to be 4115.43 Pascal. Now mole fraction, if we have to find, in terms of your partial pressure, it can be found out. So this will come out to be, this is your mole fraction. That is X for your fuel is 0.0406. Okay, so this is your question number 16. Then is your question number 17. Find the air fuel ratio of the mixture in the room. Air fuel ratio we have to find out. For that, first let's find this. This is 1 minus x of f. That is 1 minus 0.0406. This. This comes out to be this. So air to fuel ratio of the mixture that is in the room is x of air into molecular weight of air divided by x of fuel into molecular weight of fuel. This is 0.9594 into 29, that is molecular weight of air, then 0.0406 into 16, that is of fuel. So this comes out to be 42.83. This is the air fuel ratio of mixture. So this is your question number 17. Then let's see what is question number 18. Oh, sorry. So find the equivalence ratio of the mixture filling the room. So equivalence ratio now you have to find out. For equivalence ratio, we need the stoichiometric air to fuel ratio. And for that, we'll have to balance the combustion equation. This. A B, C, D. So first, if you balance carbon, then B becomes 1. Then 2B plus, to balance the carbon. If you balance the oxygen, 2B plus C equals to 2A. Okay. Then this becomes 2 plus C equals to 2A. Okay. So we are not, because we are not bound to, because the value of A is not bound by any constraint, so we can keep it. Okay, if you see H, let's see H. So H is 4 equals to 2C. From here, your C equals to 2. Okay, so using this here, A equals to 2, B equals to 1. And then for N, this is simple. D equals to 3.76 because A is 2. So this is your balanced equation. Okay. So this, if you have to find, this is equal to mass of air by mass of fuel, right? So this can also be written this way. Where z equals to x plus y by 4 and x and y are from this here. So if you do this, z comes out to be 2. Okay. Now if you place this z equals to 2 here, then this becomes air to fuel 2 divided by 1 into 29 by 16. So if you solve this, this will be 17.255. Now, so equivalence ratio phi is air to fuel stoichiometric, air to fuel in actual. So this will be 17.255 divided by 42.83, and this comes out to be 0.4028. So this is your answer. Okay, so if we see, this is 4028, but please do check the calculations, and if there are some mistakes, please do write down on the comment box. Okay, so this was it. This was the last question of this session. So we will conclude the session. So this question, session was session number 11, live tutorial session number 11 of Advanced Thermodynamics and Combustion, being conducted by IIT Guwahati under NPTEL. And the theme of today's discussion was combustion and flames, where in the first lecture we were introduced to modes of combustion, where we saw premixed and non-premixed type of flames, and where what are the various properties linked to a particular laminar flame, and how the flame velocity gets affected, by different factors involved. After this, we next move on to lecture number 29, where we saw uh, flame arresting methods basically, and the flame stabilization methods. Flame arresting methods like quenching, then minimum ignition energy, and third one also, which was flammability limit. Okay. After this lecture, the last lecture was on your jet type of flame that we see in our household ovens. Okay. Cooking ovens. And here we discussed laminar diffusion flame and its structure also. After that, we moved on to some conceptual questions. We did 15 questions, theoretical questions based on the this week's content, and after that, we did 3 questions based on the paragraph, and the questions were from stoichiometry. And this way, uh, we did our today's session. Okay, so now that we have come to the end of session, I'll say thank you, and I'll take leave. For the next session, the timing remains same, and the day also remains same, that is Sunday. And other than this, a course concluding session has also been arranged. It will be a 2-hour session where I'll briefly discuss all the topics that have been covered in the whole period of this course of Advanced Thermodynamics and Combustion. That will be the last live session of this course. Okay. So till then, goodbye and keep learning. Thank you.